So the buffer overflow, actually this part is an interesting topic. And however, this is a powerful tool that can be used by attackers. And we look at buffer overflow at the previous, like in the previous topics. For example, the ping of death is a buffer overflow. And then later, for the malware, we can see some malware actually they also use buffer overflow to do the like a spreading or infection. For example, some worm, they actually use buffer overflow to spread itself among the network. So we will see some other examples. Alright, so what is a buffer? So buffer is basically some space in the memory. Right? So when we write a computer program, so when you declare some variable, and when you actually compile the program and run the program, then when you run the program, then for the variables you declare in the program, we will allocate some space in the memory for that variable. So this is called the buffer. Right? So buffer overflow means when you try to assign some value to the space, to the buffer you allocated for this variable, if the space, say the value actually you assign is larger than what the buffer can store, then basically what the input will overwrite some other content in the memory. So in this case, we have a so-called buffer overflow. So that's a simple explanation about this term buffer overflow. Right. So essentially, when you declare integer, for example, in like C or C++, then you will reserve like a 32 bits, 4 bytes. In the memory. When you run the program, actually 4 bytes will be reserved for this variable, right? So when you declare array, then you have, for example, you have a character array with size 10, then 10 bytes will again be allocated for this array in the memory. However, so if you try to assign something which is exceeds the size of the buffer, then basically the content will overwrite some other content. So this is how buffer overflow can happen. So when you try to assign some value, then basically this value will be written into the memory, into the buffer. But if this, in this case, so if this is like a normal value, then nothing happens. But if you have a value which exceeds actually the size of the buffer, then you will have a problem. So buffer overflow, this is a definition. A condition at the interface and which more input can be placed into buffer or data holding area than the capacity allocated, right? So basically you put more input than the capacity of the buffer. So in this case, you will overwrite other information. If the information is critical, then you can have a problem. All right, so the attacker can exploit this kind of buffer overflow to either crash a system or even gain control of the system. So the crashing a system actually can cause problem, but if the attacker can gain control of the system, it's even worse, right? Because the attacker can do a lot of malicious activities. So let's look at a simple example. Suppose we create a structure or like a character array and also integer. So in this case, so when you run the program, then if you declare a variable, with this type, then in the memory we will allocate a buffer for this structure. We will allocate 8 bytes for the name, this character array, and then integer, like 4 bytes, 32 bit for the student number, right? So later when you try to assign the values to those variables, for example, so you create 2 records for student A and student B. So student A, you assign a number, student number like this, and the name David. And then student B, you assign again a different student ID and a different name. Right? So what do you expect to see in the output? Right? So if you output the student name and the student number, so what you will see is like something like this. For David, everything is normal. It will show name David, and then student number like 1, 2, 3, 4, 5, 6, 7. But for Alexander, Now the name is correct, but the student number is something random, right? Something random. So why we can't see the correct student number? Because if you look at this structure, the character array actually contains only 8 characters, right? The character array contains only 8 characters, but Alexander, actually this name contains more than 8 characters. And in the memory, actually we put 8 bytes for the name and 4 bytes for the student number. But if this string is larger than 8 bytes, then this string will overwrite the student number. The student number now becomes something random, because it's overwritten by this name, which is longer than the buffer, right? So if you look at the previous picture, basically, if the name is longer than the buffer here, then it will overwrite this part, the student number. Then when you display the student number, you get a wrong answer. All right. So buffer overflow, basically, the one of the reasons for buffer overflow is because of poor programming practice, or like a poor programming behavior or habit. So if you do some sort of handling, error handling or exception handling, actually you can easily detect buffer overflow. Right? So for C and C++, actually buffer overflow is a major problem. But for some other high-level language, like Java, C#, actually they will do some checking to prevent buffer overflow. So when you use C and C++, then you need to pay attention for the buffer overflow. Right, so buffer overflow actually can be used to perform different types of attacks. So as mentioned in the NIST definition, so you may crash a system, and in a more advanced attack, the attacker may be able to gain control of the system. So we will look at some example how this can be done by using buffer overflow. How does the attacker gain control of the system? Right, so we will see some examples. Okay. So basically, one typical example, so which is related to the topic we studied yesterday, is the attacker may, if let's say we have a root user, the root user allows the attacker to execute a program. In this case, actually the attacker can use buffer overflow to open a shell. If the attacker can open a shell, and then if say this program has a set UID, then the shell opened by the attacker will have root privilege. In this case, the attacker can do anything, right? So that's something related to what we studied in the previous lecture. Right, so some other examples, for example, in this is one of the old operating system. So if we use a buffer overflow, actually we can overwrite the privilege mask, because in this OS, actually the privilege mask is put after the username, right? So in this case, actually, if you give a long username, you can overwrite the privilege mask. Then basically you can gain more privilege than what you should have. Right, so some other examples, we will also look at some of them later when we look at, for example, the malware, like worms, how to use buffer overflow to spread the worm across different networks. Right, so this is another simple example. So if say you have a buffer which has only capacity 256, but now you try to assign a string which is longer than the buffer, then of course you will have buffer overflow. And in C and C++, actually there will be no when you run the program, so they will not handle this kind of buffer overflow for you. All right, so you may ask, then why? So this program looks silly, right? So you have a buffer 256, but you try to assign array which has a string which has 521 characters. But imagine, so here is not a constant. If this here is the input from the user, so here the 512 is replaced by the input. For example, the input to this function. So then in this case, actually, this buffer overflow can really happen, because the user may give a wrong input. The attacker may give deliberately give large values and the buffer. Then in this case, you can have a buffer overflow. Right, so to handle this kind of buffer overflow, actually one simple technique is to do the error handling or exception handling. So basically you can just do a check whether this boundary of the buffer is exceeded or not. If it exceeds the boundary, then you can just give an error message or you just exit the program. Right, so this is a standard way to prevent buffer overflow. Right, so we will look at some examples how buffer overflow actually can crash the system or gain control of a system. So we will look at the stack overflow and the heap overflow. So we will first look at stack overflow, and then we will look at the heap overflow. So stack is some space in the memory we keep for the local variable and the return address of a function. When you call a function, we will create a stack for the function, and then we will store all the local variables and then return address and so on in the stack. Right? So if we have a stack overflow, then we can override the content. For example, you can override the return address. If you override the return address, then you may not return to the original function which calls this function. You may return to a different function. You can execute a different function. Right? So that's how we can perform malicious activities by using stack overflow. Heap overflow actually is for the dynamic variables. If you declare dynamic variables, those variables will be put in the so-called heap. Okay, so we will look at both problems for a buffer overflow, stack overflow and heap overflow. So here is basically the rough picture about the memory structure, right? So if you have a program, basically you have this is a so-called PCB, process control block, and then you have the machine code of the program here, and then you have all the memory here to store the variables, and also to store you can have the global variables, global data stored here. You have the a local variable of the program stored here, and then you can have this is for the variable of a local for a function, local variable of a function. And for dynamic variable, you store them in the so-called heap, right? So this is basically the structure of memory. And the stack actually grows from top to bottom, and the heap actually grows from bottom to top. So we have the spare memory in the middle. So this is how we manage the memory for a program. Right, so when you call a function or you run a program, actually some memory will be reserved in the so-called stack. So the stack actually contains the local variables and also the return address. The return address actually is the address where the control will be returned after you finish running the function. Right, so in general we have the stack pointer. The stack pointer basically will point to the current location in the stack. Right, so this pointer will be updated. For example, when you add a new variable, it will just push the new variable into the stack. Right, when you read the variable, it will pop the variable into out of the stack. So this is essentially the same as the stack data structure. Right, you push variable and you push data and pop data. Okay, so this is how when we do a function call, so how the stack is created and then managed. So for example, we have a function P. So function P will call function Q. Suppose P is a function, and P will call a function Q. So P may be a function called by another function, say the main function. The main function will call this P. P then will call Q. Suppose this is a scenario. So in the stack, this is a stack for function P. Right? So in function P, we have the return address. So the return address is pointing to somewhere where you should return the control after you finish function P. For example, in the main function, somewhere you call this function P, then after you finish the execution of P, you return the control to the main function, to the next command, to the next statement after the invoking of function P. So this is where you return the control after you finish function P. Similarly, so if P calls Q, then this is a return address in the function P. That means after you finish function Q, So the control will be returned to function P to the position where you call, after you call, the position after you call, you have this invocation of function Q. Right, so let's see how the stack actually is created. So when function P try to call this function Q, actually it will first push the parameters for the call function onto the stack. So these parameters will be pushed onto the stack of P. Right, and then you will execute the call instruction. Then this basically will push the return address into the stack of Q. So basically the stack of Q now will start with the return address. That means when you finish Q, you should return the control to this address, where is this address is somewhere in the machine code of function P. Right. So now basically you start to allocate the content for this function Q. Right. So then the function Q will push the current frame pointer. So the frame pointer is pointing to the start position of the stack. So we have 2 pointers. One is a frame pointer. It points to the current stack, so the starting position of the stack, right? And then another one is the so-called stack pointer. So it will move, but the frame pointer will remain unchanged. It's always pointing to the start position of the stack, right? So basically, it will need to change the frame pointer because before you call the function Q, frame pointer is pointing to the beginning of stack P. But now, if you call function Q, you need to move the frame pointer to this new position for stack Q, right? And then you also store the old frame pointer here. So basically, here you store the original frame pointer in function P. The reason is because if you finish the execution of Q, you need to restore this frame pointer back to this position. So that's why you need to store it here. Later, you can restore this frame pointer back to function P after you finish the execution of function Q. So that's why we need to store the frame pointer to this old frame pointer, this field. Right. So after that, basically now you can set the frame pointer. After you store the old frame pointer here, then you can now originally the frame pointer is pointing to this stack. Now it points to the stack of Q. Right, so now you can allocate the space for local variable. For example, you declare some local variable in function Q, then it will be allocated. These variables will be allocated in the stack. Right, so actually after you finish executing function Q, all these local variables will disappear because all the pointers will go back to function P, and then this part of memory actually becomes inaccessible. Right, so after you finish function Q, then all the pointers will go back to the stack of function P. Then you can no longer access the local variable here. So that means that in function Q, if you declare some local variable, after you finish are gone. So you can't access the variable anymore. So you allocate the buffer for the local variables when you execute the function Q, and then you can run the program, the machine code of function Q. So after you finish the execution of function Q, then basically it will start to set the stack pointer and frame pointer back to function P because you finish Q now. You need to restore these pointers back to P because the next step is you will return to P and continue the execution of function P. So you need to restore all these pointers back to the stack of P. Right? So basically you need to pop up the old frame pointer, and then you basically, for example, because the old frame pointer is stored here, you can retrieve the value here. Now basically reassign the frame pointer back to a function P. Right? So then actually after you restore the frame pointer, you can find where to return, where the control can be returned in this return address. Right, so then the control will return back to P, and everything here now becomes not accessible. You can no longer access anything in the stack of Q because now all the pointers are pointing to the stack of P. So this is how we allocate the memory when we call a function, right? Okay, so why we need to introduce the previous part? So actually the previous part shows the return address actually is put together with like the variables, right? So then if someone try to assign some malicious value for the variable, then this malicious value, malicious input, if buffer overflow occurs, then this content will overwrite the return address. If the return address is overwritten, then after you finish executing this program, this function, maybe you will return to some random address, or maybe you will return to somewhere where the malicious code is placed. In this case, either the system will crash, or some malicious code will be executed, right? So instead of the original control, the code that should be returned. So in this case, you may change the return address by providing some like malicious input to overflow the buffers. Alright, so this is basically how the buffer overflow can happen. And the one important fact that allows this buffer overflow to occur is when we fill the data, when we try to like store the data for the variables, the direction is from bottom to top. So that means in the previous picture, actually, here is top, here is bottom, right? But when we actually assign the values, it's in this direction. That's why I just turned the picture upside down. So I put the bottom here, the top here. So the fill direction is in this direction. So this is very critical, because if we fill the content of the variable, the buffer, in this direction, then if buffer overflow happens, then for example, if you assign something longer than the buffer, larger than the buffer of this variable, then it will overwrite local variable 1. So if you say you have a larger like input for the local variable 1, it will overwrite the return address. So in this case, actually, we can either crash the system or change the return address to an address of malicious code. In that case, the control will now return to the malicious code, and the attacker now can perform some attack. So this is why the buffer overflow actually can cause damage, because the attacker can either crash the system or even gain control of the system. So we will look at some examples. So this is an example to illustrate how this return address can be overwritten, because if the buffer say only have a 16 byte, but you have a longer string, then the buffer will be overwritten, and then, sorry, the return address will be overwritten, and then you will have a buffer overflow. So here, pay attention to this string copy. So just now, some student asked me, so in the previous part, we also looked at this string copy, and there is a comment saying string copy is bad. Why is string copy is bad? Because this kind of function will not check the boundary for you. If you have a buffer which is smaller than the input, even if you try to copy the longer string into the small buffer, this will still go through. The string copy will not check the boundary for you. So that's why we highlight this function. Actually, not just the string copy. So there are some other functions in C and in like a C string functions. They will also have the same problem. So they don't check the boundary for you when they allocate the inputs into the string. Right, so one scenario here, one possible outcome here, if we have a buffer overflow, so one possible outcome is basically the system will crash. Right, so this is the simplest attack. However, so if the attacker actually performs some more advanced attacks, they can even do more malicious actions. For example, they may change the return address to a specific one instead of random address. So the specific address can be somewhere in the system or can be somewhere in the buffer. Right? So this is basically more dangerous. So the attacker actually can allocate some malicious code here and then change the return address to here, to the buffer. Then you will execute the malicious code here. So you use the malicious code as the input, and then you override this return address. Then basically after you finish the program, the return will the control will be returned to the malicious code you inserted in the buffer. So in this case, the attacker can basically do anything, right? So this is how we can use buffer overflow to perform to gain control of a machine, or to open a shell or execute some extra function which is not supposed to be executed. So we can do all these kind of activities if we can overflow we can overwrite the return address, right? So you can even insert some code because you overflow the buffer. So you can insert some malicious code in the buffer, and then you point the return address to the malicious code you inserted, right? So this is basically what I just mentioned. So when you override, when you do the buffer overflow, you can insert, for example, the machine code for this command, which essentially open a shell. So after that, you overwrite the return address. Now you point, after you finish the program, the control will be returned to this position. Then this malicious code, which actually opens the shell, will be executed. So remember, in the previous lecture yesterday, we looked at this set UID, right? So set UID means, say, if a program is created by a root user, and then the root user actually puts this set UID, this flag on. That means anyone who executes this program will have root permission. So in this case, suppose the attacker prepares some malicious input, and then the attacker basically uses the buffer overflow to launch such an attack. So basically you put the machine code for opening a shell inside the buffer, and then you overwrite this return address to the starting address of this machine code. Then after you finish the program, something extra will happen. Basically, a shell will be opened because now the control actually returned to this position. A shell will be opened because the set UID actually is the flag is on. Then when the attacker opens this shell, actually the attacker has the root permission. If you open a shell with root permission, then you can do anything, right? You can modify the shadow file. You can add some new users and so on. So you can do any activity, right? So basically, in this case, the attacker can cause more damage than simply crashing the system, right? So if you just crash the system, then we have a denied service. But if you can open a shell, then you can gain control. For example, you can simply add a new user account, and then you grant that user account the permissions for accessing some secret information and so on. So you can do all those kind of attacks. So string copy is one of the functions, and these are the other functions you need to pay attention because they do not check the boundary. They do not check whether the input is longer than buffer or not. So you need to be careful when you use these kind of C string functions. Right, so let's look at one example, how this, one typical example, how this buffer overflow can be used, for example, to execute some function which is not expected to be executed. Right, so in this function, so we have in this program, we have this function x. Right, so this function x is the function that it should be executed. Right, so however, there is another function y. So we don't call this function y in the main function. So y should not be executed. However, so if we can use buffer overflow, although we only call function x here, we can invoke function y. So although the main function here only invokes x, but we can invoke function y as an additional function to be executed by using buffer overflow. Right? So how can this be done? So in this case, the x function actually will print the stack. So this is to illustrate how the attack works. But in general, in reality, you may not be able to do this. So you need to use some other way to find the return address. For this program, because to illustrate the effect, we print the stack to show how this buffer overflow attack works. So to print the stack, actually you can simply use this this command. So basically, it will print the content of the stack pointer. So the stack pointer will pop up data, and then you can look at the content. Okay, so remember the goal here is to invoke function y, which is not supposed to be executed by the main function. Alright, so if we run the function, say we run this function with input hello, alright? Now in this case, actually the buffer overflow does not happen. So basically the content will be written to the stack correctly, right? So first we will basically the program first will print out the starting address of x, starting address of y, and then it will show the stack of function x, right? So this is the original stack. After you assign the hello to the buffer, to the variable, then the stack will be changed to this. For example, here you can see hello is written into the stack. So 48, this is corresponding to h. Like 65 is corresponding to letter E. So you can see the field direction is in this direction. So H, E, L, L, O. And then the C string always ends with this non-character, right? You have this non-character to end the C string. So this is where we, so after you assign hello to the variable, you can see actually the content of the stack is changed. Now hello is in the stack. So this is a normal expected like a behavior. So you just print this stack for a given string. Okay. So now what happens if you use a string longer than the expected like input size? So in this case, basically you can see the stack now will be we will have a stack overflow. So everything here will be overwritten by this long string. And then eventually, then the system will crash. That means the program will abort. And then you will see error message. If you look at the offset here, basically you can see offset is the string you use to overwrite the return address. Right. So this is what you will see after if you have a stack overflow. Right, so here is another example to illustrate like so this is to show that, so pay attention to this character, which is always used to denote the end of a string, right? So if you just do 20, you will still crash because although the buffer has a size 20, but it will still crash because you have an additional non-character here to end the string. Yes?
So if the size is 20, then do we have to consider the fact that we need one extra?
Yeah, so this is to show that even if you have 20 character, you have an extra end of string character, then it will still overwrite the return address, then you have the system crash.
So this means the size still must cannot exceed 20, right?
Yeah. So including the end of string, the non-character.
So what if it's 19? What if we?
If you have 19, then you will have no problem. Yeah. So, right. So in this case, what if I put something special here? Where I don't use a random A string containing all character A. I put a special content here. The special content actually is the address of function y. So in this case, if you put this input, then you will fill the buffer with all the A, and eventually you will also put this address into the return address. So now if you put this address into return address, then the function y will be executed, then you will see this string. Right, so this is basically what the function y does, right? Function y is just to print this string, but you can do other operations here if you want. So if you want to do other malicious actions, you can put those malicious actions here. So basically, here you can invoke a function y, which is not expected to be executed. So here you need to pay attention. So the function y has address like this. When you try to fill the buffer, fill the this stack, this return address. So you should do it in a reverse order. So you have 40 here, 13 here, 28 here. Right? So the order is just opposite to the address here, because you fill the buffer in this direction. Right? So you put 28 here. So you will first put 28 here, then you put 13 here, then you put 40 here. Now this becomes the same as the address of Y. So that means here you need to put the opposite, use the opposite direction for the address. Alright, so this is one example to illustrate. So if there is some function, and we do not expect to call the function, however, you can use buffer overflow to run the function. Okay, so this is one example. Right, so you may ask, then, in this case, how about we run this program in a different machine? Because different machine may have a different address. Right, so this is basically how you attack the program by using this return address. Then you may ask, can this program still work if I run the program in another machine? You may say the answer is no, because in another machine the address may be different. But actually, if you run the program, no matter which machine you use, it will always work, because the address we saw in the program, actually the address is a logical address, not a physical address. So if you study operating system, you know. So basically in the PCB, in the process control block, we have the offset. That is where the starting address in the physical memory is stored. And then we only need to care about the logical address. So logical address is used in the program. So even you change to a different machine, then the code will still work, because we don't change the logical address when you run the program in different machines. You only change the physical address. That means the starting point. You only change the starting physical address of the program when you run it in a different machine, but the logical address will remain the same. That means because in the attack we always use the logical address. So in this case, even if you change to a different machine, the attack will still work. So eventually, the program, if the program is vulnerable, anyone who runs this program can be attacked by using this buffer overflow. Alright, so this is about stack overflow, and the next part we will look at this is basically the simple case, because we provide the stack, the information of the stack, right? So you may ask then, how about if I want to execute something which is not in the program? Because the function Y is originally in the program. So if I want to execute something outside the program, for example, I want to open a shell. So the original program is just to maybe print some data from a file and so on. So now I want to do something which is originally not in the program. Say I want to open a shell. How to do that? So in this case, you need to insert the malicious code inside the buffer. And then you change the return address to the starting position of the inserted malicious code. Alright, so maybe we look at that part in the next class. So that's another example. So we call that such kind of, in particular, if you want to open a shell, you want to just open a shell, maybe to run some command, then you can use the so-called shell code. So the shell code is basically the code that will open shell, and we will insert that code into the buffer, and then we try to run that code when we finish some program. So that's what we will look at in the next class. So how to insert malicious code and run the malicious code. So in the first example, actually, it's still not realistic, because we give you the program and we just call the function within the program, right? So, but a more realistic attack is to insert malicious code. Right. Okay, let's continue the topic of buffer overflow. So yesterday we looked at this attack. So actually the buffer overflow will be used in different ways to either crash a machine or gain control of the machine. So we look at one example. So when you have a program, actually you only want to execute X, So if you like grant the execution permission to other users, so you only want to let other users like run function X, but actually if you use buffer overflow, then you can override the return address, and then people can actually run some additional function within the program. So then, so before we look at some other like ways to use buffer overflow to attack the computer, then what are the methods we can prevent, for example, stack overflow or buffer overflow? So actually some methods are already used in different systems, like Windows system, Unix system, they actually use some of the method. So some can be applied to stack overflow, but some other method can be applied to different like buffer overflow attacks. Right, so how to prevent? Actually, there are two different like aspects in terms of prevention. So we can look at the prevention from the perspective of the developer, like the programmer, and then also we can look at the perspective of prevention from the user. So for the programmer, actually, so the way to prevent buffer overflow is to write your code carefully and don't be lazy. So if you want to use one of those functions like string copy, string concatenation, and so on, so try to check the boundary first before you call the function, right? So don't just ignore the like exception handling or error handling. Try to make like try to add some like if statement or some like checking before you call this kind of insecure function, which can cause buffer overflow, right? And then you can also use compiler tools. So for example, actually some of the compilers, including the Visual Studio, they provide some so-called stack guard. So if you have this like a Visual Studio, you have this stack guard, this option on, then actually it will provide some mechanism to provide prevent buffer overflow. So one particular way they actually used by many compilers is to put a so-called guard value or so-called cookie. Sometimes people call it cookie, some people call it a guard value. So basically the idea is before actually you put some some secret like value just before the return address. So in this case, this secret value should not be accessed by any piece of code within the program. Alright, so and this secret value should be unknown to the attacker, unpredictable by the attacker. So in this case, if the attacker basically use buffer overflow to change the return address, they will change this value because the value is unpredictable. So if it's changed, then the system will notice there is a buffer overflow because the normal program, so there is no like a code that will access this value or change this value. So if this value is changed, that means buffer overflow occurs. And there's many compilers actually they allow you to compile the program using this kind of guard value to protect this return address, right? Also, if you want to use some C string function, then you can either like develop your own like function. Actually, you can simply develop a secure version of the like string copy by yourself. So you can call it like a string copy 2. So in this case, you call the string copy, but you try to check the boundary. So in this case, you can develop a new version of a string copy by yourself. And in some libraries, they also provide the some safe functions to handle strings. Right, so for the end user, then of course, for the end user, so what you can do is to do like testing, and then you try to remove some like vulnerable software. So if you are unsure about the software, say if you don't just install like software blindly. So if you are unsure whether the software is secure or not, so you try to avoid installing software, and then do the testing before you actually use the software, right? So similar as default deny, we should have a default not install policy. Right, so run the software at least privilege required. So don't use set UID, for example. So if you have a program and you are the administrator, you are the root user, so when you grant the program to other users, for example, you allow other users to execute the program, don't use the CSCI2. So if possible, don't use this CSCI2 because other people may get your privilege, your permission. Right, so apply the patches like updates from the software developers. So this can also prevent the vulnerability. So the original software may have some vulnerability, but the patch may basically address the problem. Right, so filter like traffic from firewall because later we will see actually some buffer overflow like caused from the attacks from network. So if basically pin of that is one example, later we will see some worm actually they also use buffer overflow to basically attack the victim's machine. So if we can have some mechanism that can prevent this kind of package from entering the network, then you can also prevent buffer overflow, right? And testing, of course, is one important tool for the user to see whether the program is vulnerable to buffer overflow. For example, you can if the program asks you to give a character string, so you can test what happens if you put some special input. So if the program asks you to give some integer, then you can try to enter some characters and see what happens. And then maybe you can test a longer string than the requirements. So you can do all types of testing to check whether the program is vulnerable or not. And one particular testing method is called fuzzing. So fuzzing is automatic testing, basically. So there is this is mainly a software engineering concept. So for software testing. So actually you can install some fuzzing software. They will do the automatic testing. They will generate different types of inputs and then try to test the software. So in this case, you do not need to manually generate the input. So you can use some software to do the testing. All right. So now let's look at some information related to the content we studied in access control, and also this part is another type of buffer overflow. Actually, it's a more powerful buffer overflow. Basically, in this case, we try to insert some malicious code into the buffer and then change the return address to the starting position of the malicious code. That means the malicious code does not exist in the original program. And now you inject some malicious code into the memory and then run this malicious code by changing the return address. Right. So we will use a particular example to illustrate this attack. This is called shell code. So shell code basically means it will open a shell. It just opens a shell. So if say the program is owned by the root user and you have set your ID, then if you open a shell, then basically this person who executes the program will have the root permission, and then the user can do anything using the shell. Right. So this is one typical example. So this is the C++ program that will open the shell. However, this is not the code we will inject into the memory. So what we will inject is the machine code. That means you first need to compile this code into a binary code, machine code. Then you inject the machine code using buffer overflow. So you call a program, and then you put the machine code as input. You basically insert the machine code inside the buffer of the program. Then you change the return address to point to the starting position of the machine code. Now, after you finish the program, then this injected machine code will be executed, then a shell will be opened. So that's how the attack works. Right, so why just open a shell? So basically, if you remember the CSCI2 problem, if the user who runs the program can get root permission, then opening a shell allows the user to do anything in the system. Okay, for example, the user can change the shadow file, change the password file, and so on. Okay, so how does the attack work? Basically, you first need to compile this high-level code, like C or C++ code, into a machine code. So this is basically the assembly code. corresponding to the program. Alright, so this is basically what you will insert. So the assembly code can be converted to the instructions. So each instruction in the assembly code actually will be corresponding to one of the machine code here. So 1 byte here is one instruction. Right, so basically now what you need to do is to insert this machine code into the program. So how to do that? Right, so this is one example from the textbook. This is a heap overflow. So how to do that? So here shows if we want to insert the code into the heap, so instead of stack, so you can use a similar method to insert code into the stack, but we use this heap overflow to illustrate how this can work. So basically, see, this is the program, right? So again, you may need to find out what's the function performed by this program, and then you need to find out where to put the malicious code, where to change the return address. And this is not as like straightforward as we saw in the previous lecture, because in this case you only have the executable file. You don't have the source code, so you need to use some method. For example, either use reverse engineering to discover the source code, or you need to use a debugger to basically do some analysis for the code. Alright, so to find the return address and find where to to put the malicious code actually is not as straightforward as in the example we saw in the previous lecture. So suppose we have such a program. Suppose the attacker knows, okay, basically we have assumption, we never trust closed source. That means the attacker can access can identify the source code. So now basically what this program does, first there is a structure. So in the structure there is a buffer. So this is where we will insert the malicious code. So the buffer has 64 characters. And then inside the structure there is another pointer pointing to a process. Right? So the process that will be executed. So this basically will point to the process that will be executed. So essentially it will point to address, the starting address of a process. Right? So now we have a simple function. Here the simple function is very simple. It will just display the length of the buffer. So the length of the string you put in the buffer. So in the main function, basically you will declare one structure, and then basically you will ask the user to enter the input. Then the input will be inserted into the buffer, and then basically you will run the program. So the program that is originally designed to run is this program. So you just, after user inputs the buffer, inputs the string to buffer, you just call this program to display the length of the buffer. So basically you just, you get the user input, then you run this process. The process actually now is assigned to this function. That means you basically, in the structure, so the process is assigned to the address of this function. And the buffer is from user input. So user give input, then this function will be executed by calling the process here. Right? So this is the original intention. We just measure the size of the input. However, so the buffer overflow actually can be done to run some malicious code. For example, to open a shell. So if you look at this is basically the malicious code that will be inserted by the attacker. So if you look at this code, it's essentially this code. So it's essentially the code we just compiled from this program which will open a shell. So we insert this code now basically into the buffer. So in this case, basically you will need to you write a Perl script. So the Perl basically will now inject this malicious code into the buffer, and then it will change the return address to the address of this malicious code. So here is the return address that will be changed. Right, so in this case, basically if you look at the previous slide here, so now we change actually the function that will be executed to the malicious code instead of this function. That means when you run this program,
this function will not be wrong because now this value has been overwritten. This address originally pointing to this function now is overwritten to a new address. So the new address now is pointing to the malicious code here. Basically, inside the buffer, you put the malicious code. So you overwrite the original address, which will print the length. You overwrite this address for the function to print the length. That's the original function we want to run. Now you change the address, this address to the address of the malicious code. So in this case, so basically, the malicious code will be executed here. Right, so if you run this Perl script, then basically, if you run this Perl script, then this malicious content will be injected into the buffer, and then the return address, originally the address should be the address of this function to show the length, and now it's overwritten by the address of this malicious code. Then the malicious code will be executed, that means a shell will be opened. After you open the shell, then you can just basically display who the user is. In this case, it will show the because now you open a shell. So the user will, when you print, you give this command who am I, then it will show it's the root user. Then actually now you can see the shadow file. You can see all the content in the shadow file, right? So because you open a shell with the root user root permission, so you can see everything in the shadow file. So in this case, actually, we inject some malicious code into the buffer and then change the address to the malicious code. Right? So this example illustrates actually Overflow is more powerful than the examples we saw yesterday. So it can be used to launch more advanced attacks. Right? And then here you may ask what are these like the 90? So you can see this is a machine code we compiled from the program. There are a list of 90 in front. So 90 actually means no operation. So that means it's like a dummy operation. We do not do any operation. So why we put a set of 90 here? Because as far as the return address point to one of those positions, then basically you will just run these dummy operations, and then after you finish all the dummy operation, you will start to execute the malicious code. That means the return address actually does not need to be specific. As far as the address falls in this range, then the code will be executed. Because if say the return address now point to this position, you will run a list of dummy operations, then you execute the malicious code. If it point to this position, it will again run some dummy operation, then execute the malicious code. So here the 90 is for no operation. Basically, the CPU just perform like a dummy operation. So in this case, you can actually there is a range you can set for the return address. As far as the address is correct, that means the address falls in that range. Then eventually you will have the malicious code executed. So you do not need to have a very specific address. You can use any address that actually falls in the range of the code. So that's why we put a lot of 90 here. So later we will see this again. So many attacks will put this kind of no operation inside the malicious code. In this case, actually the attacker does not need to have a specific address. As far as you can find a range, find the address that is within the range, then you can run the malicious code. Because so if say that the pointer points to here, the control returns to here, then you will just run 90, 90, 90, 90. So these operations perform no operation basically. But after you finish the last 90, then you will start to execute the malicious code. So this is the malicious code we compiled from the source code. So the same malicious code. Okay, so this is basically how we can insert some malicious code, like the shell code. The shell code basically just open the shell, and then you can run like you can gain control of the machine by opening a shell, and then you can like change the password or insert a new account and so on. Right. So this is the last example. for buffer overflow. So okay, so how do we know the address? As I said, this is not a trivial task. So how to find the address? You need to find, for example, one way is you find a way to crash the system. Then the debugger can be executed. So you use the debugger to find out where the address is. So it's not as easy as in the example we saw, because in the example we saw yesterday, it will print the address. But in this case, you need to use some additional tool to find out where the return address is. Right? So that's why I said it's not as trivial as shown in the slide. So one critical step is to find where is the valid return address that can execute this malicious code. So basically, you need to, for example, use a debugger or use some other tool to find out what's the memory location for this program, and then you need to allocate what is the range you can use as an address to execute this code. But the address here can be any address within this range. So you can start with any position here, then actually it will still work. Right, so that's why we insert many 9-0 here to make sure the address can be a range instead of one address. So that's the last example for buffer overflow.